we are in three-dimensional space, and the temperature at a point with coordinates x, y, and z is given as follows. How can we find the rate of change or the gradient at this very specific point? Well, we need to know what the gradient first is, right? And this is what the gradient is. So if f is differentiable, then the gradient is just the vector which holds all the partial derivatives with respect to all of the variables. So it is a function of n variables. First coordinate is the partial with respect to the first. Second coordinate is the partial with respect to the second, and so on. I'll actually keep this, and I'll minimize that. So let us compute this gradient t. I've very conveniently wrote it like this. Maybe I shouldn't write f in that case, I should probably write t. Then we don't really have n variables, we just have 3. I hope you don't mind if I do like this. And these 3 variables are x, y, and z. So maybe I should write x, y, and z. And then maybe I should start computing them. So the partial derivative with respect to x of this thing means that we fix everything else that is not x, and we take the derivative with respect to just x. In that case, these would be coefficients in this exponent, and we would only need to multiply by the derivative of this exponent, which is going to be minus 2x. So to be more precise, the derivative is but this time it's going to be with respect to x. Maybe I write prime. Maybe if I want to be very, 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 very precise, I write partial x. And quite similarly, we will have the same for y and z. The same logic. But not with x, of course, it's going to be with y and with z. That is just the derivative of e to the minus x, or e to the function of, so we're just using the chain rule. And the reason why we don't care about the derivative of the outside function is because the derivative of the outside function is the outside function itself. So this is good. Take the partial of this with respect to x, you get minus 2x. Take the partial of this with respect to y, you get minus 6y, and here you get minus 18z. Now this is only in the bracket to be very clear. I don't want to write the whole term once again, and at the same time I don't want to erase it. So I do like this. We're not just looking for this gradient, we're looking for the gradient at a very specific point, which is 2, minus 1, and 2. And so it might be a good idea to compute this. So we're going to have 200 and then it's going to be minus 2x. X is equal to 2. I should probably multiply by 2. Then we have e to the minus x squared minus 3y squared and minus 9z squared. So I'll write this on the side. So minus 2 squared minus 3 times minus 1 squared minus 9 times z squared, which is 2. What does this whole thing give us? Well, luckily we have a calculator for us. We don't need to compute this on our own. This is equal to that. It's equal to the following. Bear with me, please. That's minus 43. Let me check this. Yeah, minus 43. In other words, I can write e to the minus 43 in all of them without really having some sort of, hurt conscience or something like that. And then it's 200 times minus 6 times this value for y, which is minus 1, times e to the minus 43. For z, we'll have 200 times negative 18 times the value for z, which is 2. And then it's e to the minus 43. Computing these three values, we will get minus 800 e to the 43 minus 43. And then this will give us 1200 e to the minus 43. And then the final one will be 36 times 200. I think that's minus 7,200. That's correct. To the minus 40. So that's the answer. It's a simple computation. The goal of evaluating it at a specific point is not to force you to go through this sorcery, but rather it's because we have a set of choices and we want you to choose the correct one. So it's more of a way to have a multiple choice question which involves this type of computation. But nevertheless, this is really the important computation. You need to be able to do this on your own. You need to know what a gradient is for that, for sure. So I hope now that you know what a gradient is, and from my side, I have nothing else to say.